Ok, bienvenidos. Soy Juan Pablo Barrer, en nombre de la Comisión de Conferencias de la Sociedad de Ingenieros de Petróleo SPE de la sección Argentina. Es un placer presentar este seminario virtual titulado Machine Learning Application for Optimizing Real-Time Drilling and Hydraulic Fracturing. Agradeciendo especialmente a Yuxin Ben, disertante distinguida de esta conferencia, así como al apreciado programa Distinguished Lecturer de la SPE Foundation. El propósito del programa de disertantes distinguidos es proporcionar a las secciones de la SPE oradores destacados, así como reconocer sus contribuciones profesionales. El programa promueve la misión de la SPE de recopilar, difundir e intercambiar conocimientos técnicos. Está financiado principalmente por la Fundación SPE a través de donaciones de los miembros, así como una contribución de Offshore Europe. La SPE agradece a las empresas que permiten que sus profesionales se desempeñen como conferencistas y al apoyo adicional de AMI, the American Institute of Mining, Metallurgical and Petroleum Engineers. También se agradece a los sponsors de este ciclo de conferencias de la sección argentina de la SPE Internacional. En la categoría Oro, a Pan American Energy y Plus Petrol. Y en la categoría Plata, a San Antonio, Total Energy y a YPF. Aprovechamos para mencionar las próximas conferencias virtuales y sin costo para socios y no socios de la SPE, divulgadas a través de la página web de la SPE Argentina, así como en LinkedIn, Instagram y redes sociales. El 11 de abril a las 12 horas tenemos la conferencia Exploración Offshore en Argentina de YPF de los expositores Sebastián Arismendi, Valeria Cohenes, Tomás De Biasi y Diego Astengo. Y el 21 de abril a las 18 horas la conferencia de To Increase Production, Listen to Your Well del disertante distinguido Dr. Luis Quintero. Conviene destacar que para socios de la SPE hay muchas más conferencias de disertantes distinguidos, así como acceso gratuito o con descuento a educación en línea y conferencias. Suscripción gratuita a Journal of Petroleum Technology y a 6 Technical Papers cada año, así como una extensa red internacional para networking y avance profesional. A continuación, los dejo con Eugenio Ferriño, quien será el presentador de esta conferencia. Adelante, Eugenio.
Bueno, muchas gracias. Como ustedes saben, los datos son el nuevo petróleo de hoy y la industria petrolera como nunca necesita todas las capacidades de las nuevas tecnologías de la revolución 4.0 para lograr los niveles de eficiencia, competitividad que estamos requeridos para sostenernos en lo que es la transición energética que estamos viviendo. Es por eso que, como nunca, este seminario que se titula Machine Learning Application for Optimizing Real-Time Drilling and Hydraulic Fracturing es un tema súper vigente y que responde a las necesidades actuales. Esta exposición primero presentará el Machine Learning y sus aplicaciones en la industria del petróleo y del gas de los últimos años, y luego compartirá las experiencias y los aprendizajes de 3 ejemplos de perforación y fracturación hidráulica en tiempo real. La presentación concluirá con varios puntos importantes, incluidas las futuras direcciones de la investigación que se está llevando a cabo y el desarrollo para las aplicaciones de Machine Learning en la industria del petróleo y gas. Quien diserta, y ya fue presentada, la doctora Yuxin Ben, es ingeniera en yacimientos de la compañía Occidental, donde desarrolla física híbrida y soluciones basadas en datos en el grupo de tecnología de ingeniería de subsuelo. Fue la principal disertadora de tecnología de Machine Learning en las plataformas de fracturación hidráulica y perforación en tiempo real de Anadarko. Ganó el premio del mejor artículo en el LURTEC 2019 y fue seleccionada como la conferencista distinguida del DSPE en el 2021 y por eso la tenemos hoy aquí. Antes de Anadarko, la doctora Ben se desempeñó como experta técnica para el software de fracturación hidráulica de Baker Hughes, ENFRAC, y desarrolló también un modelo de fracturas complejas para Halliburton y realizó un postdoctorado en el MIT. Así que ven el nivel de la disertante que estamos presenciando. Y la autora es autora de más de 30 artículos, posee 3 patentes estadounidenses, obtuvo una licenciatura de mecánica teórica en la Universidad de Pekín y un doctorado de ingeniería química en la Universidad de Notre Dame. La presentación tiene una duración estimada de 45 minutos. Será brindada en idioma inglés, pero hemos pedido a nuestra expositora que lo haga de la manera más simple y hable en un inglés lento para que trate de ser lo más comprensible para todos. Sin embargo, si hubiera alguna consulta, los invito a que usemos el chat para en tiempo real sacarnos las dudas. Al fin, le pido por eso a todos que silencien sus micrófonos durante la presentación y al final habrá un intercambio de preguntas y respuestas. Por favor, todo aquel incluso que tenga alguna pregunta y la quiere ir adelantando, incluso si se anima, adelante, hágala en idioma inglés para que la vea Yuxin Ben, y si no, la hace en castellano y nosotros con todo gusto la traduciremos para ella. Sin más, la dejo con la doctora. Welcome, Yuxin Ben. We are very proud of having you here. Come on, please. You can start your presentation when you want. Thank you very much.
Yes. Thank you for the introduction. Yeah, although I don't understand the Spanish. Let's see. Okay. Can you see my screen?
Yes, yes, perfect.
Okay.
If you can put in presentation mode, please.
Okay. I need to switch this one. Okay.
Yes, It is perfect now. Thank you very much.
Okay. I would like to thank SPE Foundation's member donations and the contribution from offshore Europe. And also I would like to thank AIME for the financial support. So today I'm going to talk about some of the machine learning applications in real-time drilling and hydraulic fracturing. So first, I will introduce what's machine learning, types of machine learning. Then I will give you 3 examples that I have used machine learning in real-time drilling and real-time hydraulic fracturing. So lastly, I will share with you my takeaways and future development that I think is important. So what's machine learning? Human beings learn from experience. Machine follow instructions. The question is, can machine learn from experience? Machine learn from the data. That's called machine learning. This is a formal definition from a scientist in IBM. He said, machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. The problem cannot be solved by if-then statements. Machine learning programs adjust themselves in response to the data they are exposed to. The second definition of machine learning came from a professor. His name is Tom Marshall. He worked for Carnegie Mellon University. He said, the field of machine learning is concerned with the question of how to construct computer programs that automatically improve with experience. Machine learning is one of the ways we expect to achieve artificial intelligence. Now, I will talk about types of machine learnings. There are 3 types of machine learning. The first one is called supervised learning. In the supervised learning, we define input and output. The input sometimes is called a feature, and the output is called a label. We are trying to let the machine to find a mapping from input to output. The process is called training. Once we have this mapping, then given a new data input, we use the mapping to predict the output. In the unsupervised learning, we don't define output explicitly. We let machine to learn the data structure inside the data samples. The reinforcement learning is the third type of machine learning. while machine learn from mistakes. So if machine does something good, we give machine an award. If machine does something wrong, we give machine a penalty. Machine learning has been used in oil and gas in a lot of domains. The unsupervised learning can be divided into clustering and dimensionality reduction. So these two approaches have been used in both engineering and geoscience. Supervised learning can be further divided into classification and regression. In the classification, the output is a discrete number. So for example, we want to classify image logs, so based on type of elements. And in the regression, the output is continuous number. So for example, production forecast, giving the past production, we predict the future production. Reinforcement learning has a limited application in oil and gas, although I've seen some publications in on using reinforcement learning in directional drilling and reservoir optimization. So this talk, I will start from drilling state identification. I apply classification to drilling state identification problem. Secondly, I apply regression to predict wellhead pressure in hydraulic fracturing. Third, I combine machine learning optimization algorithm, which is called model predictive control. I use this approach to optimize real-time hydraulic fracturing cost. There is another word for this one. It's called machine learning control. So this word has been used. So this terminology has been used mainly in the outside oil and gas industry. So mainly is used in chemical engineering or mechanical engineering. There is some overlap between reinforcement learning and machine learning control. If you sometimes depending on who you are talking to, computer scientists tend to call it reinforcement learning, but the mechanical engineering or chemical engineers, they tend to call it machine learning control for the same problem. Now I will start to talk about real-time drilling. We want to build a real-time drilling platform to improve drilling efficiency and to optimize through real-time monitoring and automation. Engineers and the field crews have multiple conflicting priorities. So we really want to to build a system which can automate a lot of the workflows that the engineers do in their daily life. So this is not necessarily a machine learning algorithm. This can be streamlined the data, can be deploy a model, a physical-based model. So we want to all these things in the same platform, so for easy access, and also help by leveraging the computation power or machine learning algorithm to help engineers do some work automatically, and then they can have more time to do much more intelligent stuff. This is the foundation of a real-time drilling platform. So in a real-time drilling platform, we use sensors to collect time series data from rigs. Those sensors normally return second by second data, well, for onshore drilling. Each second corresponding one rig state or called drilling state. So the purpose is to let the computer decide automatically the rig state instead of having the engineers to label those data manually. We create a set of rules, such as about a lot of them are if-then commands. So We start from a high level, it's called a component layer, to classify the status of major rig system. And then we apply a second set of rules to determine a rig state. So on the left, I listed a couple rig state. So these may vary depending on the company. So usually the engineers inside the company will define these rig states. So the accuracy is extremely high, except for drilling. So this because in US onshore at that time we use a lot of mud motor. So when mud motor is used, the rocking is used during sliding. So that creates a challenge when we want to distinguish slide drilling versus rotate drilling. So this is the data that the drilling engineers use to identify rigs drilling, the slide drilling versus rotate drilling. So the y-axis is the rotary RPM, and the x-axis is the time. Each dot represents 1 second data, and the gray dots represent the rotate drilling, and the blue dots represent the slide drilling. So as you can see, if we use threshold, it's very hard to separate the rotate drilling from slide drilling. So this is the case when if-then command won't work. So the trick here is we use machine learning. So before we apply machine learning, we have to do some transformation. So here we convert drilling time series data into a one-dimensional image classification problem. So what we did was we use a moving window. So each window includes 20 seconds of data. So this 20-second data is our input. The output is the rig state or the drilling state. The drilling state is the corresponding to the drilling state at the last second in the 20 seconds of window. Initially, we also use the well section as one of the features when I train the model. So well section includes the vertical curve and letter. The engineers labeled a lot of data for me, so he didn't select these wells randomly. He intentionally selected different wells from different rigs and different formation to just have a good representation of the data. We apply 3 machine learning algorithms. And here I'm showing you the prediction about the accuracy of the model. So we do a training, test, validation, and yeah, these are the blend test result. If it's 100% accuracy, it's good. So the accuracy is very important for this problem because the other algorithm are based on the rig state algorithm. And if we think about if we have a well which takes about 1 week to drill, if the accuracy is 99%, we will misclassify 1.5 hours of data. Yeah, so as you can see, the random forest, there are 2 blend test wells which gives less accurate result. So we actually deploy the CNN model eventually, and the hybrid model just takes much longer time. I would like to share with you the deployment stage, so how we, went through all this deployment. So initially, we have a rule-based model, and then we put it in the system, and it gives us 70% of accuracy. And then we applied a machine learning model. So we train the model offline, and then we deploy the model in the real-time system. So every second, this system will make prediction for the rig state. And then we replace a more accurate model, which is convolutional neural network. So the lessons learned, that lesson number 1 is the data for well-bore section. So I mentioned that I use the well-bore section as a feature when I trained my previous version of model. However, in reality, when we drill a well, we have to do a survey to get the true well-bore trajectory. So the well-bore section data are not always available in real time. So then we decided to see if we can remove this feature, still keep the accuracy of the model. So luckily, accuracy is kept once we remove the variable section feature. And also during the production phase, so production meaning it's IT word here, so it's not oil production. So production meaning we train the model, we think the model is good, and then we put the model in the system. So we trained one model, and then for Delaware Basin and DJ Basin. So without including the third basin's data as a training data, we put the model to predict the rig state in the third basin, and the accuracy was lower than expected. So then I realized that we should include the data from Powder River Basin as well. It's just because Powder River Basin has different geological properties, and also the crews on the rigs may operate the equipment differently. So we included the wells from all three basins and trained one single model. So this model actually was deployed in the system and has been used by all the rigs, all the onshore rigs of my company. Here is the architecture of the real-time drilling system. So we start from a data source layer. While we collect real-time data and the static data. The static data includes something like casing size or fluid properties. And the analytics layer includes the drilling state recognition algorithm and some of the KPI analysis algorithm and some of the physical-based approach, and also we can also add some optimization algorithm. Yeah, the last layer is for data storage. So in the database, we saved all the real-time data, static data, and the calculation result from the analytics layer. And of course, we need to have a good UI in order to engage the users to use it. This is the simple user case. So we create a UI for the algorithm. So as you can see here, the gray color strip represent the slide drilling, and the black color strip represent rotary drilling, and the pink curve represent motor orientation. So yeah, this is very intuitive. So when the engineers see it, they can tell, if everything is all right. And this is a simple KPI analysis. So with this algorithm running at the back end, the engineer can compare a current well which has been drilled with the offset wells in the same rig. They can do a comparison on the footage, and also they can compare the rate of penetration between slide drilling and rotate drilling. So now I will switch gear to talk about the real-time application of machine learning in hydraulic fracturing. This slide was prepared 2 years ago, so I think right now hydraulic fracturing costs are probably comparable to drilling costs, but still it's quite high. And hydraulic fracturing cost depends on the wellhead pressure, the slurry rate, and I didn't include the FR concentration. FR uses here. That's another variables that need to be optimized. And wellhead pressure depends on the slurry rate and also depending on the friction reducer. So if we can predict the wellhead pressure, we can prevent screen out, optimize hydraulic fracturing cost in real time by adjusting the pumping schedule, and help completion engineers make better decisions in real time. So why a data-driven model? Wellhead pressure include the following contributions: bottom hole fracturing pressure, hydrostatic pressure, pressure due to pipe friction, due to perforations, and due to near variable tortuosities. There are several commercial hydraulic fracturing simulation softwares that are physics-based. And typically, in order to have a good computational performance, the software make a lot of assumptions. It cannot simulate each of the contributions very well, such as near variable tortuosity. So we can use a simple data visualization to find the correlation between the data. So these data are available in real time for the completion engineers. And the first data is a wellhead pressure, and then it's a bottom hole proppant concentration, and FR and slurry rate. So if we go into details, when the bottom hole proppant concentration went through these step changes, you can see the wellhead pressure also went through these step changes. So such kind of correlation is easy to see it by visualization, but maybe not easy to see just the from the pure data. And secondly, we can use data analysis to find the correlation between the variables. So first plot is autocorrelation coefficient plot. So we can find that the wellhead pressure actually depends on its history. And second plot is percent correlation coefficient plot. Well, you can see how wellhead pressure depends on the other variables. So if this number is 1, meaning strongly correlated. If this number is 0, meaning less correlated. So as I point out, wellhead pressure depends on bottom hole proppant concentration a lot, as I showed in the previous slide. So you can see this number is 0.91. So it's consistent with the observation. I use a neural network to build this model. My input is slurry rate, proppant concentration, FR concentration, and my past wellhead pressure. I build a model and then predict the wellhead pressure in the future. So I didn't include the geological information in the model here. So this is the first version of model. And secondly, it's because in reality, when the engineers are on the location, so the only thing they can make a change is the slurry rate, proppant concentration, and FR concentration. So the geological conditions and the job designs are already fixed. And so that's why, because we only consider those variables, so I propose to use a continuous learning approach. So this is to mimic how engineers, frac engineer does his job in the real world. So as we collect the data, we train a machine learning model. And then with this machine learning model, we make predictions. So as more data is generated from the system, we add the data to my older data and train a new model. Then we use this new model to make predictions for the next couple of minutes. So we continuously do this in order to get the good prediction. So this is one of the results. The black line is the observed pressure and the red line is the predicted pressure. So basically every 2 minutes, we make a prediction for the next 2 minutes. So I'm hoping in the future we can improve this model. Yeah, but right now it's a 2 minutes prediction. And the cones, actually, the cones, the gray cones you have seen here is due to the uncertainties from neural network. So I also checked the computational cost of such a model. So you can see the y-axis is the computation time in seconds, and the y-axis is and the x-axis is the true hydraulic fracturing treatment time for a single stage. So for a 2-stage of job, or 2 hours of a frac job, it takes about several minutes of computation time for one approach, and takes less than 1 minute for the second approach. So compared to 2 hours, I think the computation cost is negligible for this case. So this is the real-time data streaming system. This is quite close to our drilling platform. So very similar. So we have a system which can collect real-time data and static data, and we can run some machine learning models on top of that and then make predictions. Then we will have a UI to show the result. This is the details of how we can run a machine learning model, train a machine learning model continuously in real time. So this is to leverage some of the components on the cloud. So current technology, currently such kind of technology is available from all the, popular cloud providers. And also there are some startups which actually help oil and gas industry to use cloud, do such kind of work. So now I will spend some time to talk about the my third problem. So how we can optimize hydraulic fracturing cost in real time. So this is a proof of concept work. So it hasn't been used in real life, in contrast with the drilling problem. But I will show you, how we can do this, how we can potentially do this. This is the cost structure several years ago, but it changed a little bit, but still, the concept is still the same. The hydraulic fracturing cost depends on the pressure and depends on the slurry rate. And it also has some friction reducer cost and the fluid cost. So can we let the computer adjust the pumping schedule to save completion cost on hydraulic horsepower? So like a human, can we teach the computer to do this? So I propose to use model predictive control to optimize the cost. So let me give you some of the analogy to model predictive control. So this is the map of Houston. This is my home, and this is Occidental Petroleum, my work. So in the morning, if I drive with Google Map, so Google will suggest me one route, and I pick this route, so I continuously driving. And on my driving to work, there may be accident, or there may be traffic congestions, unexpected conditions. And typically Google will give me advice on how to change the road. Then I will select the options. And once I make that selection, so Google will collect the new data on that road and make another set of recommendations. Then I can decide, if I need to take a further actions in order to get to work on time. So the idea here is we want to develop a model based on existing data and make prediction about the future behavior. And in meanwhile, we need to set up some constraints, such as if there is in the field, the wellhead pressure and the slurry rate may be limited by the available pump trucks, or the proppant concentration may be limited by the design of the well-design team of your company. And that, there may be other constraints provided by the engineers. So model predictive control can consider all these things. So this is the diagram for model predictive control. On the left is the it's the past data. So we use the past to train a model and predict the future. The black line represents the target. The yellow line is the predicted output. So we want the yellow line to be as close as the to the reference trajectory, and the green lines is called the prediction. So this timeline is called the predictive horizon, and these green steps are the control input, the suggested control input. So we only execute the first step in the suggestions. And on the next step, we will retrain the model and re-optimize the process and make selections. So this is a real field case. It's not done by a machine learning algorithm. So what I'm showing you is, I hope I can include the friction reducer data in this slide, but I didn't. So the y-axis is the average pressure for each stage, each hydraulic fracturing stage. And these numbers represent the stage number. So 1 represents the stage closest to the toe, and 47 means it's more close to the heel. So we can imagine the pressure at the whole stage will be larger than the pressure at the heel stage due to wire ball friction. So you can see the pressure actually is shown like that. So what the engineers has been doing behind the scenes is they try to reduce the FR concentration as they move away from the toe. So that makes sense because you have less pressure. But you can see opportunity here because they keep the rate as a constant, and still there is 1,000 psi difference between the first stage and your last stage. So they can probably increase the rate more to finish the job sooner and save some cost. So this is the mathematical formulation for this problem. So in the control field, they call it the system identification. So it's nothing more than a similar word to machine learning. So X here represent wellhead pressure, and U represent propellant concentration, slurry rate, friction reducer concentration. A and B are parameters that need to be determined from the system identification approach. So this is the whole workflow. We start a frac job, we gather some data, and then we will train a machine learning model. With that model, we can make predictions for the wellhead pressure. If the pressure is high, there is potential screen out, then we may suggest to cut sand or stop pumping. If there is no potential screen out, we can run the MPC optimizer. So the optimizer will give some recommendations on the value of manipulated variables. Here are friction reducer, propellant concentration, and slurry rate. So we can, choose the first step of recommendations and execute. Then, meanwhile, we collect more data. So we train a new model to make new predictions. And then we check the screen out. And then if there is no screen out, we do the optimization. So we continuously do this until the job is done. So this is the proof of concept running in MATLAB. So I set up the constraint on the pressure, so which is the delta pressure. The pressure change is 50 psi. So these are the suggested values on slurry rate, FR concentration, the propellant concentration. So in reality, so this cannot be true because typically in reality, these numbers have their own constraints by the conditions I described before. But this is just a proof of concept. And this one is I set up constraint is delta P is 50 psi again, but I give a constraint on the maximum propellant concentration and also maximum incremental propellant concentration, and then I run this MPC control. MPC optimization. So let me conclude by several takeaways. So the first one, what we have done here, I give you some of the examples that we applied machine learning. What we have learned mostly is machine learning can perform much better than rule-based model. So if we apply machine learning to the right problem. And secondly, a successful machine learning application requires a lot of good collaborations between people with different backgrounds. And also, most importantly, I think for real-time drilling and real-time hydraulic fracturing, it's very important for the scientists to collaborate with the operation team. So it's those people who will use the algorithm that scientists develop. So we have to closely work with them and then to think about how we can use our intelligence to improve their efficiency of doing their job. This is the second takeaway is for algorithm development. I think machine learning has to be combined with physics. Oil and gas industry has been existing for many years. We have accumulated a lot of knowledge, domain knowledge, as well as good physical-based models. So we should combine those with machine learning in order to leverage machine learning better. And there is a new emerging field called physics-guided learning or physics-informed learning. So where people use a neural network to solve partial differential equations instead of the common numerical approach, such as finite difference or finite volume method. Oil and gas industry right now, it's very changed a lot, and the oil and gas price, nobody can predict oil and gas price. I think the efficiency is very important for the industry to survive. Machine learning can be combined with optimization algorithm to optimize each of the engineering domains from drilling, hydraulic fracturing to reservoir to production. And also, as I practice machine learning more, I think statistics actually is very, very important because in oil and gas, we don't have big data. Quite often we have missing data due to some measurement error, or it's just that the data is not good. You hardly can. The current technology doesn't allow you to measure those type of data, or we don't have a lot of data. We only have small data set. In these scenarios, we have to apply statistics to really make the machine learning make sense. And third, I think the infrastructure-wise right now, I think it's quite mature. Is really up to the companies on how quickly to adopt these technologies. And I saw, the startups have been working on solutions on these options. The last takeaway is about risks and remedies. Machine learning is based on the data. And a lot of time, the data may not cover, the available data may not cover all the scenarios. So then we have to think about how to do it. And in case of failure, it might be very difficult to establish responsibilities. And also, in the data, when we generate the data, it may has hidden bias. We, as a human being, we always have bias. And the data may be contaminated by, by just the misfunction or dysfunction that's sensors. I think we should use our engineering judgment, and we can set up alerts in the system to identify outliers. We can also establish liabilities between service companies and operators. And lastly, I think it's important for us to calibrate with other industry to learn their best practices. So these are the references that include the materials I talk about today. And lastly, your feedback is very important. You can scan this QR code and give feedback to SPE. Thank you for your attention.
Okay, thank you, Yuxin. Very interesting, your presentation. We have some questions from the audience. The first one is, do you have projects of ML for automatic directional drilling real time? This means to make the system decide when slide or rotate to decrease the tortuosity problems?
Well, for us, probably, well, for our company, we don't have it. Although it was on our roadmap when I was working on this problem, but we wasn't able to do it because of the acquisition by the new company. Yeah. But I think a lot of on the drilling side, a lot of the service companies, especially service company, are working on that solution.
Okay, thank you, Yuxin. Another question is, how do you determine pH proppant concentration?
It's measured from the in real time a bottom hole proppant. Oh, it's calculated. It's a calculated number, bottom hole proppant concentration.
Okay, thank you.
Yuxin, it was an excellent presentation. Thank you very much for sharing this with us. Actually, I have two questions regarding this. First of all, is if you or your company, at the moment that you make this research, or maybe today, you have some KPI about the improvements or the savings that you can get in the drilling, in the total cost of drilling. That is question number one.
I don't have a number currently.
No, not in dollars, maybe percentage of, or not in money, maybe in time.
Well, I can give you of time-wise, like for this particular problem I talk about. So when the engineer labeled the data for me, he labeled about I think 30 wells. It took him 9 to 10 hours, a whole weekend, basically. Yeah, so imagine if you want to do hundreds of wells, that will take you a lot of time.
Okay, yeah. Then if I understand it, you right, what you are saving it is engineering time, but not drilling time. I mean, the well, it is gonna take the same time of drilling.
Then it's a hard to determine the number, right? The typical practice is it's up to the operation team, right? After they have seen the difference, and then they will try to figure out how to save the time. Yeah.
Okay. And second question is, do you know if there's some project like this in Oxy or some similar like this where you are participating, or maybe some fellow regarding geosteering and improving geosteering in real time, or also the geometric of the well real time, because that is also a topic a lot of discussions regarding real time machine learning
yes,
applications around well construction.
Yeah, then I don't have enough knowledge on that topics. I know people is doing that just as you know it, but I don't know. Yeah, there are. I think in Oxy they have this operation geology team, so that's I'm guessing it's part of their jobs. I don't know how they use that technology. Yeah, but we did have that function.
Something that it is discussed around this is as well as you make a drilling plan, and then thanks to the machine learning and techniques as you presented in real time, we can improve it. Also, it is true that geologists design a well and expect some response from the geosteering and the geologist data. But while the people are drilling the well and are performing the geosteering analysis, maybe they can find in real time some changes. And it is also discussed if we can use some kind of artificial intelligence to help to make those decisions in real time.
Yeah, I believe so. This is it's a multi-team problem.
Okay.
And the industry has been talking about, when you talk about artificial intelligence, digitalization, they always talk about people stay in the silos and keep talking about that, But I hope the situation will change more, but gradually, yeah.
Yep. Okay, the challenge is there.
Yeah.
Juan Pablo, is there some other question?
Yes, people are thanking you a lot, Yuxin. Very good presentation and very nice comments about the presentation. And there is another question that says, is it possible to do a model to recognize if there is interference between the actual well and the nearest well?
You mean frac hit or
I think
yeah.
I think it has to do with the frac hit and parent-child optimization.
Right. Yeah. Yeah, you can. Yeah, I think somebody already done a lot of the jobs on that regard. Yeah.
Okay. Well, Eugenio, I think this we are not having any more questions, so I think we can be very grateful with Yuxin. Very nice having you here and very interesting your presentation.
Thank you for having me here.
Yes, and also please keep in touch because the topic that you are studying and working, it is very interesting. It's for sure some area where we expect a lot of advances in the short term. And then please, if through SPE, we will keep following you and we expect to having you presenting a new work like this very, very soon.
Thank you for the encouragement.
Okay. Bye-bye, Yuxin.
Bye. Yeah.
See you.
Thank you again. Yeah.
Bye-bye.
Have a good evening.
Okay.
Thank you very much. See you.
Yeah. See you.